In the previous video, we walked through the hydraulic calculation of a fire sprinkler system. Even though the results showed that the water supply could meet the system demand, this video will demonstrate how thoughtful optimization can significantly reduce costs without compromising performance. For the first step in optimizing the system, let's consider using quick response sprinklers. Before we look at how these sprinklers affect the overall system demand, we'll briefly review the NFPA 13 requirements for using quick response sprinklers across different hazard occupancies. According to Section 9431, spray sprinklers installed in light hazard occupancies are required to be of the quick response type. Therefore, standard response sprinklers are not permitted. This requirement is based on the superior performance of quick response sprinklers in achieving life safety objectives. Given the nature of light hazard occupancies, which often have higher occupant loads, life safety is a paramount concern, making the quick response requirement especially critical. NFPA does not impose restrictions on sprinkler response type in ordinary hazard occupancies. Therefore, either quick response or standard response spray sprinklers are permitted. However, Section 1023 prohibits the use of quick response sprinklers in extra hazard occupancies where the density area design method is applied. This limitation is intended to prevent the simultaneous operation of an excessive number of sprinklers due to the faster response characteristics of QR sprinklers. In our example, since the occupancy is classified as ordinary hazard, we're permitted to use quick response sprinklers. As explained in the design area adjustment video, when the system is a wet pipe system, the ceiling height is up to 20 feet. There are no unprotected ceiling pockets larger than 32 square feet, and there are no unprotected areas above a cloud ceiling. We're allowed to reduce the design area based on the ceiling height. In our project, the ceiling height is 10 feet. Using either the formula or the adjustment diagram, we find that a 40% reduction applies. This brings the final design area down to 900 square feet, which corresponds to just 8 sprinklers. After running the hydraulic calculation, we find that the flow demand drops to about 209 gallons per minute, and the required pressure decreases to roughly 49 pounds per square inch. That's a reduction of roughly 40% in flow and 38% in pressure. In general, reducing the system flow rate offers several advantages, such as smaller water tank capacity and reduced pump flow. In our example, it also positively impacts system pressure in 2 ways. First, as the system's flow demand decreases, the water supply can deliver higher pressure according to its supply curve. As shown in the online tool video, when using standard response sprinklers, the available pressure at the system demand is 85 pounds per square inch. By switching to quick response sprinklers, the total system demand decreases to 459 gallons per minute, allowing the water supply to provide 91 pounds per square inch. The same principle applies to systems supplied by a fire pump. Based on the pump's pressure curve, it can deliver higher pressure at lower flow rates. The second benefit relates to reduced pressure loss through the backflow preventer. This loss is flow dependent and decreases as the flow rate decreases, as indicated in the manufacturer's performance chart. In general, increasing the flow rate through a backflow preventer leads to higher pressure loss. However, there is a transitional region where the pressure loss temporarily decreases as flow increases before rising again at higher flow rates. In our example, when we switch to quick response sprinklers, the reduced flow demand also lowers the pressure loss through the backflow preventer, which helps to slightly reduce the overall pressure requirement. As explained in the earlier video, increasing the sprinkler's K factor reduces the pressure needed to achieve a given flow. We also covered how to choose the most suitable value for a design. In the HC tab of the online hydraulic calculation tools, you can simply choose the appropriate K factor. In our example, the minimum acceptable sprinkler flow is 24 gallons per minute. By entering this value in the flow rate field, the software recommends a K factor of 8. Let's see how this change affects the system demand. For the most remote sprinkler, using a K8 requires 9 psi to discharge 24 gallons per minute. In comparison, a K5.6 sprinkler needs 18.4 psi to deliver the same flow. This means the required pressure drops by 9.4 psi when switching to the larger K factor. Although the required pressure at the most remote sprinkler drops, we shouldn't expect the overall system demand to decrease by the same amount. As we move to the subsequent sprinklers in the design area, the larger K factor causes each one to discharge more water, and that increased flow creates additional friction loss in the piping. As a result, some of the pressure savings gained at the first sprinkler are offset by higher losses throughout the system. For example, sprinkler 102 in our project discharges 25.4 gallons per minute with a K5.6 sprinkler, while with a K8 it discharges 26.8 gallons per minute. This increase in flow from sprinkler 102, along with the higher discharge from the other sprinklers in the design area, results in more water moving through the piping, which in turn creates additional friction loss. When we run the hydraulic calculation using quick response sprinklers with a K factor of 8, the system demand comes out to approximately 225 gallons per minute at 43 pounds per square inch. This represents about a 16 gallons per minute increase in total flow and a 6 psi reduction in required pressure compared to the system using quick response K 5.6 sprinklers. In other words, the 9.4 psi savings at the most remote sprinkler ultimately results in a 6 psi reduction for the entire system, with 3.4 psi of that savings lost to additional friction loss caused by the increased flow. The hydraulics of the system, both flow and pressure, become worse if we move to a larger K factor. For example, if we use a K factor of 11.2, the system demand increases to 309 gallons per minute at 65 pounds per square inch. This is why we must select the K factor carefully. Increasing the K factor may reduce the pressure required at the most remote sprinkler, but the higher flow rate can cause the system to lose both pressure and flow. So far, we've explored using quick response sprinklers with a K8. Since QR sprinklers are generally more expensive than SR sprinklers, and K8 sprinklers cost more than K5.6, it appears that our optimization has actually increased the system cost and conflicts with the primary intent of hydraulic calculation, which is cost savings. However, this change creates a larger safety margin in the required pressure, and that extra margin allows us to begin reducing pipe sizes, which ultimately brings the overall system cost down. Reducing the pipe size not only lowers the cost of the piping itself, but also decreases the cost of fittings and labor, and even speeds up the installation process. Since Section 28212 specifies that the minimum pipe size for black steel is 1 inch, we begin with 1 1/4 inch pipe and reduce it. As expected, this adjustment increases the pressure demand to 54 pounds per square inch and reduces the safety margin to roughly 35 pounds per square inch. In the second step, we reduce the 1 1/2 inch pipes in the branch lines and the riser nipple to 1 1/4 inch. With this change, the pressure demand increases to 62 and the safety margin decreases to 28 psi. Since the water supply is still capable of supporting this pressure, this level of optimization is acceptable. Now let's examine what happens if we reduce the 1 1/4 inch pipes to 1 inch. With this change, unfortunately, the required system pressure exceeds what the water supply can provide. If this optimization were possible, All of the branch lines could be reduced to 1 inch, eliminating the need for reducer fittings and making the installation process much easier. As we know, adding a fire pump to support the required pressure is not a reasonable option in this case, since it would impose additional cost on the system. Therefore, we'll look for a method that allows us to keep the advantages of using 1-inch branch lines without adding significant costs to the system. There are 3 common piping methods used in fire sprinkler systems: tree, looped, and gridded. In a tree system, there is only one path for water to travel through the pipes to reach the sprinklers. These systems can be arranged in several configurations, including center-center feed, center-end feed, side-center feed, and side-end feed. In looped systems, there are 2 paths for water to travel through the pipes to reach the sprinklers. Because the flow is distributed between these paths, less water travels through each one, resulting in lower friction loss. As a result, the hydraulics of a looped system are more efficient than those of tree systems. A gridded sprinkler system can be a hydraulically efficient method of water distribution, as it allows multiple flow paths to supply the operating sprinklers. This results in lower friction losses compared to tree or looped systems. However, the hydraulic calculation of gridded systems is more complex when performed by hand because the flow distribution within each pipe must be solved iteratively. In practice, modern sprinkler design software performs these calculations efficiently using node pressure and Newton-Raphson-based solution methods rather than classical Hardy-Cross techniques. It's important to note that in dry pipe systems, double interlock systems, and all types of pre-action systems used in storage, except miscellaneous storage, NFPA 13 prohibits the use of gridded piping. This restriction exists because the multiple flow paths in a grid can increase the time it takes for water to reach the operating sprinklers. Let's go back to our example and change the side-end feed to the center-end feed method. Since the cross main is located at the center, both design areas shown in figures A and B are acceptable. After the hydraulic calculation, we obtain a flow of 236 gallons per minute at 60 pounds per square inch, with a safety margin of 29 pounds per square inch. As we can see, selecting the appropriate piping configuration can significantly impact the system's hydraulics. Now that we have a good safety margin, let's continue with pipe sizing optimization and reduce the size of the cross main, feed main, and riser from 2.5 inches to 2 inches. The hydraulic calculation now shows a flow of 238 gallons per minute at 93 pounds per square inch, with a safety margin of -3 pounds per square inch. This indicates that the water supply cannot support the system demand. If we could optimize the pipe size to 2 inches, in addition to reducing the cost of pipes, fittings, and installation, we could also reduce the cost of riser components, including the flow switch, wet alarm, and butterfly valves. Let's explore another optimization method to help achieve these cost savings. In our project, the selected pipe type is black steel, Schedule 40. Let's assume that the cross main, feed main, and riser pipes are joined using roll-grooved connections. Therefore, in accordance with Section 16322, these pipes are permitted to be Schedule 10. As we know, increasing the pipe schedule leads to an increase in wall thickness. Since the outside diameter of a given nominal pipe size is the same for all schedules, we can conclude that decreasing the schedule increases the inside diameter of the pipe. Based on the Hazen-Williams formula, as the inside diameter increases, the pressure loss per foot of pipe decreases. Using 2-inch Schedule 10 black steel pipe for the cross main, feed main, and riser results in a system flow of 237 gallons per minute at 84 pounds per square inch, with a safety margin of 5 pounds per square inch. Further pipe size reduction causes the water supply to no longer support the system demand, so we stop the optimization. In this video, we examined several optimization methods for reducing system costs. However, these methods are not limited to what we have explored. In some cases, changing the sprinkler type or even the sprinkler coverage may be beneficial. Depending on the pipe type and size, using the Darcy-Weisbach equation instead of Hazen-Williams for friction loss calculations, as well as accounting for velocity pressure, may also be helpful. We will cover these topics in the upcoming videos. It is important to note that although the use of quick response sprinklers was very helpful in our example, in projects with ceiling heights greater than 20 feet, we are not permitted to take advantage of their design area reduction. Therefore, using quick response sprinklers in such cases may only increase the system cost. As another example, while many assume that eliminating the fire pump is always one of the best cost-saving solutions, in large projects with weak municipal water supplies, this can become a false economy. Without a pump, the system often requires significantly larger pipe sizes throughout the building just to minimize friction loss. The material and labor costs of these oversized pipes often exceed the cost of the pump we were trying to eliminate. In addition, smaller pipes are faster to install and easier to route. Finally, it should be said that each project dictates its own unique optimization approach, and there is no one-size-fits-all solution for every design. That level of engineering judgment is exactly what makes fire sprinkler design so fascinating.